Hello, you're welcome back. All right, so this time around, we're going to look at a practical on optical lens. Okay, so as usual, we are going to look at the relationship between the theory, okay, and the practical implementation of optical lens. And I believe that you know what an optical lens is actually used for. All right. Okay, an optical lens is actually used to produce image of an object, okay, by means of refraction. Okay, so through refraction, an optical lens actually produces the image of the object. Now look at the experimental setup here. So I now have a convex lens. The lens we are using here is convex lens. Okay, it's either you call it convex lens or you call it a convergent lens. Now, why is it a convergent lens? It's called convergent lens because the rays of light, okay, coming from or parallel rays of light that passes through the lens will always converge at the principal focus. Okay, and unlike a mirror that produces image by reflection, a lens produces image by refraction. Okay, so what is the whole idea of this optical lens experiment? Okay, we are to investigate the focal length of the lens. So we are going to actually vary the object distance, then we'll get the corresponding image distance from the lens. Now, the apparatus that we actually use for this experiment, here we have a candle, okay, that actually serves as the object. I have the optical lens, convex lens, okay, that is fixed inside the lens stand just to make it stand around, and then I have a mirror. All right. Now, the whole idea of the mirror is I will use it as a screen to be able to get the image of the object. So one of the things that you should actually be careful about, know, right, the image that is actually formed, the difference between the image that's formed by the mirror based on the reflection, okay, based on the rays coming from that of the lens. Okay, so you should be able to know that. All right, so now, okay, and of course you know very well that we are not going to conduct the practical. We are going to see how we use, okay, we use the idea of theoretical formula to populate our table. Okay, so that's exactly what we're going to do here. So now what is the formula for an optical lens? Now the formula goes this way: 1 all over f is equal to 1 all over u plus 1 all over v. Okay, so which simply means that if we are to conduct this experiment, we actually vary the object distance. Then as we change the object distance, we also use the mirror, okay, on the screen to locate where the image of this object is being formed. Then we'll now record it. Okay, so now this is how this is going to be the table. All right, we'll find the object distance, then we get the corresponding image distance, then we'll find the reciprocal 1 all over u and 1 all over v. Okay, so now in this same scenario, we need a constant that will help us. All right, for us to be able to use this formula, we need to know the focal length of the mirror that we are using. All right, so we need to know the focal length of the mirror we are using. So how will we be able to get the focal length of the mirror you are using? You can still get the focal length of the mirror you are using this formula. Okay, so all you just need to do is you conduct the experiment just one time. Conduct the experiment one time. Let's measure the object distance, okay, then locate where the image is being formed. All right. And in most cases, the image you get for a convex lens is always inverted. So that's one way you differentiate the image that is formed by the lens, okay, or the one that is formed by the reflection of the mirror. So the image mostly formed by a convex lens is inverted. So by the time you get that inverted image, the distance of that inverted real image, okay, inverted real image, then you can actually use this formula now to get the focal length. 1 over f is equal to 1 over u plus 1 over v. So once you have just conducting the experiment one time to get the focal length, all right? In most cases, most lenses, laboratory lenses, the focal length is 15 cm. And that's what we're going to be using, okay? So once you just find the focal length 15 cm, the rest of the practical now, you don't need to actually touch the practical instrument. You just use this value and get what you're looking for. All right. So with this value now, let's actually populate our table. Right. So we're going to find the corresponding image distance. Then we get the reciprocal. Now let's start with. I'm going to start with. Okay. Let's start with lower values. Or should we use this value? Okay. You can choose any value, any range of value you wish, okay, depending on what is given. Okay, so I gave myself 5, 10, 15, 20, 25. So starting with 5. Okay, so I want to get the image distance. So that means the object is 5. So from this formula now, making 1 over v the subject, 1 over v is going to be equal to 1 all over f. Then this goes over, that's going to be minus 1 over u. So I'm going to give you a shortcut, okay? The shortcut that will actually help you find v directly without going through the process of evaluating with LCM, okay? So once you have this kind of fraction and you want to get v, just use this principle, product all over difference. Product all over difference. So that's going to be the product of f and u, then that divided by the difference, u minus f. So f is 15, u, we started with 5, then divided by the difference, okay, which of course is going to be 5 minus 15, okay, 5 times 15. Okay, I believe we need to actually work with calculator. All right, here we go. 5 times 15. Okay. Then divided by minus 10. That should give me minus 7. But that's minus 7.5. Okay. So minus 7.5. So why do we have minus 7.5? Minus 7.5 actually shows that the image is actually real, okay? The negative value actually, okay, shows the negative value shows a virtual image, please pardon me, okay? Normally a concave lens actually forms image, okay, at the refracting surface that is should be behind the mirror. So when the image form is behind the mirror, you locate it behind the mirror, it is actually real, okay? So the value is always positive. It is always real and inverted. And okay, so in most cases you always locate the image of the object behind the mirror inverted, okay? But there are some cases where you have it in front of the lens, please pardon me, and at that point it is said to be virtual. All right, so you locate it, you locate that in front, and it is virtual. It's said to be a virtual. So in this case now, because I have minus 7.5, that's virtual image. So here I have minus 7.5. So let's go with 10. Applying the value here, that's 15 times 10, then 10 minus 5. So I'm having 150. 10 minus 15, please order me. 150 divided by minus 5, that should be minus 30, if I'm not mistaken. Okay, 150 then divided by 5. Okay, minus 30. Okay, am I making a mistake? Let me look at the very first value. Okay, there seems to be 15 times 5. 15 times 5 divided by 10, that's minus 7.5. Okay, so here I have 15 times 10. Okay, so then 15 times, in this one here, I have 15 minus 15 will give me 0. This should be 0. This should be 0. Then I now go. So the next value, I'm having 15 times 20 divided by, this time around, 20 minus 15. Okay, so 15 times 20. 20 minus 15 is 5. Then divided by 5. 60. So this time around is positive 60. 25. 15 times 10. Then 25 minus 15, that is 10. So divided by 10. Okay. Positive 15. 1, 2, 3, 4. Okay, the last one. 15 times 30. And of course, 30 minus 15. That's 15. So divided by 15. 30.